What if I told you the universe has its own way of playing tricks on us? Picture this. You're gazing up at the night sky, and suddenly you spot the same star in two completely different places. No, your eyes aren't deceiving you. This is the cosmic magic of gravitational lensing, a phenomenon so extraordinary it bends the very fabric of reality. Thanks to theory of relativity, we now understand that gravity doesn't just pull objects. It warps space and time, twisting light like a funhouse mirror on a galactic scale. And here's the wild part. This isn't just some abstract idea. Massive objects like galaxies and black holes act as natural telescopes, magnifying and distorting light from distant corners of the cosmos, revealing secrets we'd otherwise never see. Think about that for a second. The same force that keeps your feet on the ground is also out there, sculpting the light from stars billions of light years away. It's as if the universe handed us a pair of glasses to peer deeper into its mysteries. And the discoveries we've made thanks to this cosmic quirk are nothing short of breathtaking. From spotting galaxies so far away their light has traveled across eons to uncovering hidden pockets of dark matter, gravitational lensing has rewritten our understanding of space itself. But how does it all work? How can something as intangible as gravity twist light into illusions that defy logic? That's exactly what we're diving into today. This isn't just a story about physics, it's a journey into the heart of relativity, where time and space intertwine to create spectacles beyond imagination. We'll start with groundbreaking predictions, explore how astronomers turned his equations into real-world discoveries, and even glimpse how these cosmic mirages help us map the invisible scaffolding of the universe. By the time we're done, you won't just see the night sky differently, you'll feel it. Because out there in the vast, swirling depths of space, light doesn't always travel in a straight line. Sometimes it bends. And when it does, the universe reveals its most astonishing secrets. To grasp how light bends in the cosmos, we first need to understand the stage it travels across, spacetime itself. Imagine space as a vast, invisible trampoline. Normally, light zips across it in perfect straight lines, like a ball rolling smoothly on a flat surface. But place something heavy, like a star or a galaxy, on that trampoline and suddenly the fabric dips and curves. Now, when light passes near that dent, its path isn't so straight anymore. It follows the curve, just like a marble would roll around the edge of that dip. This is the essence of revelation. Gravity isn't just a tug between objects, it's the very shape of the universe reshaping around mass. But light is a curious thing. It behaves both like a wave, spreading out in ripples, and like a particle, tiny packets of energy called photons. When these photons journey through warped spacetime, they don't just bend, they slow down, speed up, and even change direction, like a hiker following a winding mountain trail instead of a straight road. That's why a massive galaxy cluster can act like a magnifying glass, twisting and amplifying the light from objects far behind it. Here's where it gets even wilder. The amount of bending depends on how heavy the object is and how close the light comes to it. A black hole, for instance, warps spacetime so drastically that light can loop around it multiple times before escaping, creating bizarre mirror images of distant stars. Meanwhile, our own sun bends starlight ever so slightly, an effect first proven during a solar eclipse over a century ago, when stars near the sun's edge appeared out of place. That single observation confirmed theory and opened the door to a whole new way of seeing the universe. So when we talk about gravitational lensing, we're really talking about spacetime itself drawing the blueprints for these cosmic illusions. The light isn't being pulled by gravity, it's simply following the curves of the stage it's moving across. And that stage, it's never truly still. It breathes, bends, and twists with every massive object in the cosmos, turning the universe into the ultimate funhouse mirror. Equations were revolutionary, but even he had his doubts. When he first calculated that gravity could bend light, the idea seemed almost too wild to be true, a mathematical curiosity rather than something we might actually see in the cosmos. Yet in May 1919, during a total solar eclipse, astronomer Arthur set out to prove it. The plan was simple in theory but incredibly delicate in practice. As the moon blocked the sun's blinding light, his team photographed stars near the sun's edge. If was right, those stars wouldn't appear in their usual positions. Their light, warped by the sun's gravity, would follow the curve of spacetime itself, making them look slightly out of place. And that's exactly what happened. The stars observed were deflected by just the tiny amounts equations predicted, about 1.75 or the width of a penny seen from 2 miles away. It was a minuscule shift, but it changed everything. Overnight, relativity went from abstract theory to observable fact and became a household name. The New York Times famously declared, "Lights all askew in the heavens," and suddenly the universe felt stranger and more malleable than anyone had imagined. What's fascinating is that himself thought this effect would never be visible beyond our solar system. The idea that entire galaxies could bend light from objects behind them seemed like science fiction. Yet here we are, a century later, using gravitational lensing to study the farthest reaches of the cosmos. Modern telescopes have spotted galaxies stretched into glowing arcs, their light twisted by invisible clusters of dark matter. We've even found the same supernova appearing multiple times in a single image, its light taking different paths around a massive galaxy before reaching us. This is the power of that eclipse experiment. It didn't just confirm a theory. It handed astronomers a whole new tool for exploring the universe. Today, lensing helps us weigh galaxy clusters, map the distribution of dark matter, and peer deeper into space than ever before. And it all traces back to that moment when starlight, bending ever so slightly, proved that space and time aren't just a backdrop to the cosmos, they're part of the show. Gravitational lensing comes in different flavors, each with its own cosmic signature and scientific superpower. The most dramatic is strong lensing, where gravity doesn't just bend light but twists it into celestial art. Take the cross, for example. Here, a single quasar blazing at the heart of a distant galaxy appears as 4 identical copies arranged in a perfect cross around a foreground galaxy. It's not a glitch in the universe. It's spacetime itself acting like a prism, splitting the quasar's light along multiple paths. These cosmic mirages don't just dazzle, they magnify. By studying these stretched and duplicated images, astronomers can peer at galaxies so far away their light has traveled for billions of years, offering snapshots of the universe in its infancy. Then there's weak lensing, the universe's subtler sleight of hand. Instead of creating bold arcs or rings, it gently warps the shapes of background galaxies, like looking through a slightly rippled window. At first glance, these distortions seem insignificant, but when you map thousands of galaxies across vast swaths of sky, a pattern emerges. Their slight bends trace the invisible scaffolding of dark matter, revealing where this mysterious substance clumps and stretches between galaxies. It's like watching the wind bend a field of grass. You can't see the wind itself, but the movement betrays its presence. Weak lensing has become one of our most powerful tools for charting the cosmos's hidden architecture, proving that sometimes the faintest whispers hold the loudest truths. On the other hand, plays out on a smaller but no less thrilling scale. Imagine a star suddenly brightening for no apparent reason. What's happening? An invisible object, perhaps a rogue planet, a neutron star, or even a black hole, has drifted between that star and us. Its gravity acts like a temporary magnifying glass, focusing the star's light just long enough for us to notice. These events are fleeting, sometimes lasting just hours or days, but they're cosmic treasure hunts. Has uncovered planets floating freely between stars, worlds with no sun to call home, and even hinted at a vast population of dark, isolated objects lurking in the galactic shadows. What's astonishing is how these 3 flavors of lensing work together. Strong lensing zooms in on the universe's most distant corners, Weak lensing sketches the blueprint of dark matter and catches the ghosts drifting through our galaxy. They're not just tricks of light, they're the universe's way of revealing its secrets, one bend at a time. One of the most breathtaking demonstrations of gravitational lensing in action is the Space Telescope's Frontier Fields project. Here, astronomers pointed at 6 massive galaxy clusters, knowing their immense gravity would act like cosmic magnifying glasses. The results were staggering. Faint, distant galaxies smeared into luminous arcs around the clusters, their light stretched and amplified by spacetime's curvature. But the real magic happened when scientists looked beyond the obvious arcs. Peering deeper into the data, they discovered galaxies so far away their light had been traveling for over 13 billion years, from a time when the universe was just a toddler. Without these natural telescopes, those ancient galaxies would have remained invisible to us, their light too dim for even to catch. Take 168-9, a galaxy cluster so massive it warps spacetime like a bowling ball on a mattress. In its grip, background galaxies are stretched into surreal shapes. Some resemble horseshoes, others spiral into glowing rings. But the most astonishing feature, multiple images of the same galaxy, repeated in perfect symmetry around the cluster's center. It's as if the universe hit copy-paste on a distant star system, giving astronomers several angles to study it at once. This isn't just a visual spectacle, it's a scientific. By comparing these duplicate images, researchers can measure the cluster's mass distribution, including the invisible dark matter that makes up most of its weight. Then there's the sunburst arc, a galaxy so dramatically lensed that it appears in 12 separate pieces across an image. Normally, this galaxy would be a faint speck, lost in the cosmic background. But thanks to a perfectly aligned cluster, its light has been 30 times, revealing details as small as 500 light-years across, unprecedented clarity for an object so distant. What astronomers found was extraordinary. Pockets of young stars bursting to life, their ultraviolet radiation punching holes in surrounding gas clouds. These stellar nurseries offer a rare glimpse into how the first galaxies built themselves, a process we'd never witness without spacetime's magnifying effect. What makes these cosmic illusions so valuable isn't just their ability to show us faraway objects, it's how they let us test the universe itself. When light takes multiple paths around a galaxy cluster, some routes are slightly longer than others. That means different versions of the same supernova might appear in our telescopes weeks or even years apart, like cosmic echoes. By timing these delays, astronomers can measure the expansion rate of the universe with precision, probing one of cosmology's biggest mysteries. Every stretched galaxy, every duplicated quasar is more than a pretty picture. It's a clue written in bent light, waiting to be decoded. Here's the thing about dark matter. Its cosmic stagehand, invisible yet indispensable, shaping the universe behind the scenes. We can't see it, touch it, or even detect it directly, but thanks to gravitational lensing, we know it's there. How? Because when light from distant galaxies passes through regions rich in dark matter, it doesn't just bend, it twists in ways that betray the presence of something massive lurking in the shadows. Picture a pane of warped glass distorting the view beyond. Dark matter does the same thing to spacetime itself, leaving its fingerprints on the light that dares to travel through it. One of the most jaw-dropping examples of this is the Bullet Cluster, a cosmic collision that handed scientists irrefutable proof of dark matter's existence. Here, 2 galaxy clusters smashed into each other at unimaginable speeds, but something bizarre happened. The visible gas, hot and glowing, slowed down and pooled at the collision center, while the cluster's gravity, measured by lensing, kept racing ahead. Why? Because dark matter, unaffected by the friction that stalled the gas, sailed right through the wreckage. Lensing revealed its ghostly outline, separate from the ordinary matter we could see. It was like watching a car crash where the passengers kept moving forward while their seats stayed behind. This wasn't just a hint. It was a billboard-sized announcement. dark matter is real and it's not tied to the stuff we know. But the bullet cluster is just the beginning. Across the cosmos, lensing has mapped dark matter's hidden architecture, revealing a vast, intricate web that stretches between galaxies like cosmic scaffolding. Without it, galaxies would fly apart, their stars scattered to the void. Dark matter's gravity is the glue holding them together, and lensing lets us trace its invisible threads. In some cases, astronomers have even found dark galaxies, clumps of dark matter with barely any stars, their presence betrayed only by how they bend light from objects behind them. What's truly mind-bending is how precise these measurements have become. By studying the subtle warping of millions of galaxies, projects like the Dark Energy Survey have reconstructed dark matter's distribution in 3 dimensions, showing how it clumps around galaxy clusters and stretches into filaments across the emptiness of space. These maps aren't just pretty pictures, they're clues to the universe's very structure, helping us piece together why galaxies form where they do and how the cosmos evolved over billions of years. And here's the kicker. Without gravitational lensing, dark matter might still be a fringe idea, a mathematical fix for odd galaxy rotations. Instead, it's now the foundation of modern cosmology, accounting for roughly 85% of all matter in the universe. Every distorted galaxy, every stretched arc of light is a reminder that the cosmos is far stranger and more wonderful than we ever imagined. The next time you look up at the night sky, remember, what you see is just the tip of the iceberg. The rest is hidden in plain sight, waiting for the right tools and the right light to reveal its secrets. Among all the cosmic illusions created by gravitational lensing, few are as striking or as scientifically valuable as the perfect circles known as rings. Picture a distant galaxy, its light streaming toward us across billions of light years, only to encounter a massive object perfectly aligned in its path. The result, a halo of light, bending around the foreground object like ripples around a stone dropped in a pond, forming a near-flawless ring suspended in space. It's relativity's most elegant parlor trick, where geometry and gravity conspire to turn a distant speck into a glowing celestial halo. Himself predicted this phenomenon mathematically, but even he doubted we'd ever see it. The odds of such a precise alignment, a distant light source, a massive lensing object, and Earth all in a straight line, seemed vanishingly small. Yet today, telescopes have cataloged dozens of these cosmic bullseyes, each one of information. Take MG 1131 plus 0456, a textbook example discovered in the 1980s. This luminous ring, nestled in the constellation Cetus, isn't just a pretty sight. By analyzing its symmetry, astronomers calculated the mass of the foreground galaxy cluster with unprecedented precision, revealing how much of its heft came from invisible dark matter. What makes these rings so powerful is their clarity. Unlike the stretched arcs or duplicated images of other lensed objects, and rings' perfect geometry lets scientists measure distances and masses with minimal distortion. It's like having a cosmic scale and ruler built into the universe itself. By comparing the ring's size to the known brightness of the background galaxy, researchers can pin down the foreground object's mass down to the last solar mass. Some rings have even revealed subtle discrepancies in their shapes, tiny deviations from perfection that hint at alternative theories of gravity, challenging our understanding of how mass warps spacetime. But the real magic happens when these rings magnify the unimaginably distant. In 2020, astronomers spotted one of the farthest rings ever found, its light traveling nearly 12 billion years to reach us. The background galaxy, amplified 30-fold by the ring's lensing effect, offered a crystal-clear view of star formation in the early universe. Without this natural telescope, the galaxy would have been a blur, if visible at all. And here's the kicker, not all rings are created equal. Some are complete, unbroken circles, while others appear as fragmented arcs, their symmetry disrupted by the uneven distribution of dark matter in the foreground. Each variation tells a story about the lensing object's structure, the universe's expansion rate, even the nature of dark energy. When astronomers find a new ring, it's not just another pretty picture. It's a puzzle piece in the grandest mystery of all, how space-time, mass, and light dance together to shape everything we see. Here's something that will bend your mind even more than bent light. Gravity doesn't just warp the path of light, it warps time itself. When a beam of light splits into multiple paths around a massive galaxy cluster, each route isn't just a different length, it's a different journey through space-time. Some photons take the scenic route, trudging through deeper gravitational valleys where time slows to a crawl, while others zip along ridges where spacetime curves less. The result, cosmic, where the same object appears multiple times in the sky, not just in different positions, but at different moments in history. Take supernova, the ultimate celestial echo. In 2014, astronomers spotted this exploding star not once, but 4 times, strewn around a galaxy cluster like scattered embers. Each image was a snapshot of the same cataclysm, but because their light traveled different warp paths, they arrived at Earth years apart. The first images appeared in late 2014, but equations hinted at a 5th encore, a delayed replay caused by light looping the long way around the cluster's dense core. Scientists crunched the numbers and predicted it would show up by late 2015. Then, right on schedule, like a cosmic alarm clock, the final flicker of its explosion blinked into view. It was relativity's greatest mic drop. Not only could we see gravity bend light, we could set our watches by it. These time delays aren't just cool party tricks, they're precision tools for measuring the universe. Normally, calculating distances to far-off galaxies involves a daisy chain of estimates, each with its own margin of error. But lensing delays cut through the guesswork. By tracking how long it takes for each copy of a supernova or quasar to arrive, astronomers can triangulate the true distance to the lensing cluster and the object behind it, no middlemen required. It's like hearing an echo in a canyon and using the delay to map the exact shape of the cliffs. The implications get even wilder when you realize these delays let us peer into the universe's expansion in real time. When light from a single event takes multiple routes, some paths stretch as space itself expands during the journey. That means the delay between images isn't just about gravity's grip. It's a snapshot of how much the universe has grown in the meantime. By comparing delays across dozens of lensed systems, scientists are building a new yardstick for cosmic expansion, one that might help settle the biggest feud in modern cosmology. Why different methods keep giving conflicting values for how fast the universe is growing. What's astonishing is how much these time delays reveal about the invisible scaffolding of the cosmos. The exact length of a delay depends on the mass distribution along the light's path, especially the dark matter we can't see. By reverse engineering delays, astronomers can weigh galaxy clusters down to the last solar mass and even map pockets of dark matter floating between galaxies. It's like deducing the shape of a shadowy object by how it distorts the ripples in a pond. So the next time you hear about a supernova appearing twice, remember, you're not just seeing double. You're witnessing spacetime itself stretch and slow, turning the cosmos into a hall of mirrors where even light can't escape the pull of gravity's stopwatch. And somewhere out there, another delayed echo is racing toward us, carrying secrets about the universe's past, present, and future, all written in the language of bent time. Quasars are like the universe's ultimate lighthouses, blazing beacons so bright they outshine entire galaxies, visible from the farthest reaches of space. But when their light encounters a massive galaxy or cluster on its way to us, something extraordinary happens. The quasar doesn't just appear once, it multiplies, splitting into duplicate images or stretching into luminous arcs, as if the cosmos itself is playing a game of mirrors. This isn't just a visual spectacle, it's a cosmic scale. Each distorted image holds precise information about the lensing object's mass, including the dark matter we can't see. Take Q0957 plus 561, the first lensed quasar ever discovered. In 1979, astronomers noticed what seemed like two identical quasars side by side, separated by just 6. At first, they assumed it was a pair of distinct objects, until they realized both had the exact same spectrum, even the same flickering brightness patterns. The truth was mind-bending. They were seeing the same quasar, its light split by a galaxy cluster nearly 4 billion light-years away. This cosmic became a stone for gravitational lensing, proving that quasars could serve as precision tools for weighing the universe's hidden mass. But quasars aren't just passive targets, they're time capsules. These objects are the hyperactive cores of young galaxies, powered by supermassive black holes devouring surrounding matter at staggering rates. The energy they release is unimaginable. A single quasar can outshine 1 trillion suns, its brilliance fueled by physics at the edge of comprehension. Normally, their extreme distance makes them little more than pinpricks of light. Yet when lensed, their faint details are, letting astronomers study the swirling disks of gas around their central black holes, or the jets of plasma shooting outward at near-light speed. It's like getting a front-row seat to the universe's most violent fireworks show, one that's been raging since the cosmos was a fraction of its current age. The real magic happens when lensing reveals quasars from the universe's toddler years. In 2017, astronomers spotted a quasar so distant its light had traveled nearly 13 billion years to reach us. But thanks to a perfectly aligned foreground galaxy, its image was 50-fold, exposing details no telescope could capture unaided. What they found was staggering. A young galaxy still in the throes of formation, its black hole already billions of times the sun's mass. How such monsters grew so quickly remains one of astrophysics' biggest puzzles, and lensed quasars are handing us the clues. What makes these objects so invaluable is their dual role. They're both the light source and the lensed probe, illuminating the invisible scaffolding of the cosmos while also serving as windows into the early universe's most chaotic eras. Every time a quasar's light bends around a galaxy cluster, it's not just creating a pretty picture, it's sketching a map of dark matter, testing equations, and revealing how the universe's most enigmatic structures came to be. So the next time you hear about a duplicated quasar, remember, you're not just seeing double. You're witnessing the universe use its own gravity as a magnifying glass, turning distant fire into a cosmic flashlight. Imagine measuring the same thing with 2 different rulers and getting wildly different answers every time. That's the bizarre situation cosmologists face with the constant, the number that tells us how fast the universe is expanding. For decades, astronomers assumed this value was settled science. But when modern measurements started disagreeing, gravitational lensing stepped in as the ultimate referee, and what it revealed has thrown everything into question. Here's the problem. One method uses the cosmic microwave background, the afterglow of the Big Bang, to calculate an expansion rate of about 67 kilometers per second per. Another approach relies on supernovae in nearby galaxies, suggesting a faster rate, around 73. At first glance, that 6-kilometer gap might seem small, but statistically, it's a chasm. These aren't just different answers, they're fundamentally incompatible under our current understanding of physics. Enter gravitational lensing, which offers a third way to measure the constant, one that doesn't depend on the cosmic ladder of assumptions the other methods require. The secret lies in those time-delayed lensed quasars we discussed earlier. When a quasar's light splits into multiple paths around a galaxy cluster, each route takes a slightly different amount of time to reach us. By precisely measuring these delays, sometimes down to a matter of days, scientists can work backward to calculate how much the universe expanded during the light's journey. It's like timing echoes in a canyon to map its shape. Projects like H0LeCOW have used this technique to nail down the constant with remarkable precision, landing somewhere between the two conflicting values. But here, where it gets really interesting. If Lensing's middle ground result holds up, it might mean neither of the original methods is wrong, just incomplete. The discrepancy could hint at something missing from our cosmic playbook, like unknown particles, dark energy behaving differently over time, or even flaws in relativity itself. Some theorists suggest we might need a new physics altogether, an extra ingredient in the universe's recipe that we haven't discovered yet. What makes gravitational lensing so powerful in this debate is its independence. Unlike other methods, it doesn't rely on calibrating distances using variable stars or assuming how galaxy clusters evolved. It's a direct probe of spacetime's geometry, cutting through layers of assumptions. And as telescopes grow sharper, lensing could finally crack the case, revealing whether this crisis in cosmology is a measurement glitch or a doorway to something far stranger. Think about what's at stake. If the constant's tension persists, we might be staring at the next Copernican revolution, a moment where the universe forces us to rewrite the textbooks. And gravitational lensing, once a curiosity of equations, is now the detective leading the investigation. Every warped quasar, every delayed supernova is a clue whispering that the cosmos still holds mysteries we've barely begun to unravel. Peering back into the universe's earliest chapters isn't just about building bigger telescopes. It's about tricking spacetime itself into working for us. Gravitational lensing does exactly that, transforming massive galaxy clusters into cosmic magnifying glasses that amplify the faintest whispers of light from the dawn of time. Take MACS 1149JD, a galaxy so ancient its light began traveling toward us when the universe was just 500 million years old. To the unaided eye, it's little more than a reddish smudge in images. But thanks to the warping effect of a foreground galaxy cluster, its light has been stretched and brightened 30 times, exposing details no telescope could ever resolve. What's astonishing isn't just that we can see these infant galaxies. It's what they're telling us about the universe's chaotic beginnings. Conventional wisdom suggested the first galaxies should be small and messy, taking billions of years to grow into the majestic spirals we see today. Yet lensed galaxies like JD defy expectations. Despite their youth, some already show signs of orderly rotation and dense star clusters, as if they matured at breakneck speed. This has forced astronomers to rethink how quickly gas coalesced in the early cosmos, and whether dark matter's invisible scaffolding played a more active role than we ever imagined. The James Space Telescope has turned this cosmic archaeology into a gold rush. By combining infrared vision with lensing's natural magnification, scientists are spotting galaxies even farther back, some as early as 200 million years after the Big Bang. These aren't just record breakers, they're stress tests for our theories. Their sheer brightness, for instance, hints at a population of massive stars unlike anything in today's universe. Behemoths that burned hot and fast, seeding space with the first heavy elements. Other lensed relics show bizarre shapes, tangled in filaments of primordial gas, offering snapshots of the cosmic web as it knitted itself together. But the real surprise lies in what these ancient galaxies reveal about dark matter's baby pictures. Simulations suggest the first galaxies should nestle inside clumps of dark matter like pearls on a string. Lensing lets us check that blueprint in real life. When astronomers map the distortions around these galaxies, they can trace the distribution of dark matter in their neighborhoods, and the results are puzzling. Some early galaxies appear to sit in halos of dark matter far denser than predicted, while others seem oddly isolated. These mismatches could mean our models of dark matter's behavior in the young universe need a rewrite, or that something even stranger, like interactions between dark matter and early radiation, was at play. What's humbling is how much we still don't know. Without lensing, these primordial galaxies would be lost in the glare of cosmic history, their stories forever untold. Now every smudge is a stone carrying encoded clues about how the first stars ignited, how dark matter sculpted the cosmos, and how the universe grew from a formless sea of particles into the structured beauty we see today. And with each new lens discovery, we're not just looking farther back in time. We're watching the universe teach us how to read its origin story in the language of bent light. Most of the cosmos isn't lit up by stars. It's cloaked in darkness where lone planets, failed stars, and even black holes drift unseen. But every so often, gravity pulls back the curtain. Imagine a rogue planet, untethered to any star, wandering the Milky Way's outskirts. As it drifts across the line of sight to a distant star, its gravity bends the starlight like a magnifying glass, briefly brightening the star by a factor of hundreds. These flashes, called events, last mere days or weeks before fading, cosmic fireflies blinking in the void. And catching them, that requires telescopes around the globe working in unison, scanning millions of stars every night for these elusive flickers. One of the most famous catches was Ogle 2005 BLG 390, a frozen world about 5 times Earth's mass, orbiting no sun. Its signal, detected by teams in Chile and New Zealand, revealed a planet so cold its surface temperature hovers near -220 degrees Celsius, colder than Pluto. But here's the twist: rogue planets like this might outnumber stars in our galaxy. Current estimates suggest there could be billions, ejected from their birth systems by gravitational tugs of war or left orphaned when their parent stars died. Is the only way to spot these nomads, as they emit no light of their own and float too far from stars to be seen directly. The real treasure of isn't just the rogue planets, it's the sheer variety of hidden objects it exposes. Some events betray brown dwarfs, failed stars too small to ignite fusion but too large to be planets. Others hint at something more sinister: isolated black holes, invisible except for how their gravity distorts starlight as they pass by. In 2022, astronomers confirmed the first unambiguous detection of a lone stellar mass black hole this way, its presence betrayed by how it stretched the image of a background star for 270 days. What makes uniquely powerful is its democracy. It doesn't favor big, bright objects. A tiny planet or a massive black hole can produce similar-looking brightenings, distinguished only by subtle details in the light curve's shape and duration. Teams like Ogle Optical Gravitational Lensing Experiment and MOA observations in astrophysics have turned this into a science of precision timing, with algorithms scanning data in real time to alert telescopes worldwide when an event begins. Sometimes, the most thrilling discoveries come from amateur astronomers who catch an anomaly in backyard telescope data, a reminder that the cosmos hides its secrets in plain sight, waiting for anyone with patience and a sharp eye. The future of this hunt is even more thrilling. NASA's upcoming Nancy Grace Roman Space Telescope will supercharge the search, monitoring hundreds of millions of stars continuously, potentially discovering thousands of rogue planets, including some as small as Mars. Each detection is a clue to the Milky Way's turbulent history, revealing how often planetary systems get disrupted, how black holes wander after supernovae, and whether our galaxy teems with worlds we never knew existed. So while galaxy-spanning lensing grabs headlines, remember, sometimes the universe's quietest whispers, a star flickering for just a few nights, tell the most astonishing stories. Black holes may be the universe's ultimate light traps, but ironically, they're also some of its most powerful magnifying glasses. Think about that for a second. An object so dense not even light can escape it can still bend and amplify light from objects behind it, like a cosmic funhouse mirror with a one-way ticket. The Event Horizon Telescope's groundbreaking image of the supermassive black hole in galaxy M87 laid this phenomenon bare. That glowing ring encircling the black hole's shadow, that's not the black hole itself. It's light from hot gas swirling behind it, warped by gravity into a perfect circle as it skirts the edge of oblivion. This isn't just a pretty picture. It's a smoking gun for relativity, proving spacetime bends so severely near a black hole that light orbits it like a car on a racetrack. What's wild is how much these lensed rings reveal. The size and shape of that ring aren't arbitrary. They're precise measurements of the black hole's mass and spin. The M87 image, for instance, showed a ring about 40 billion kilometers across, confirming the black hole weighs in at 6.5 billion times the sun's mass. But the real magic happens when you look closer. The ring isn't perfectly uniform. Its brightness flickers and dims asymmetrically, a fingerprint of the black hole's rotation warping spacetime into a swirling vortex. It's like watching water spiral down a drain, except here, the drain twists the very fabric of reality. Now here, where things get even stranger. Black hole lensing doesn't just magnify light, it can create infinite reflections of the universe. If you could hover near a black hole's event horizon and look sideways, you'd see the back of your own head. Why? Because light from behind you would loop around the black hole and hit your eyes like a cosmic hall of mirrors. This isn't just theoretical. Some quasars lensed by black holes appear as multiple images, each one a snapshot of the same object from a different angle in spacetime. But the most tantalizing possibility lies in what black hole lensing might teach us about quantum gravity. Right now, relativity and quantum mechanics are like two languages describing the universe, both brilliant but utterly incompatible when it comes to black holes. The Event Horizon Telescope's next target, Sagittarius A star at our galaxy's center, could bridge that gap. If its lensed ring shows even microscopic deviations from relativity's predictions, say, subtle flickers or fractal patterns in the light, it might hint at spacetime's granular quantum structure. Imagine glimpsing the universe's pixelated underpinnings in the warped glow around a black hole's shadow. From theoretical oddities to front-page photographs, black hole lensing has transformed these cosmic vacuum cleaners into laboratories for extreme physics. Every distorted ring, every mirrored quasar is a reminder that even in the darkest corners of the universe, light finds a way to spill its secrets. And as telescopes grow sharper, we're not just observing black holes, we're decoding the universe's most cryptic handwriting, etched in the bent light of the abyss. Simulating the universe isn't just about crunching numbers. It's about playing cosmic architect, building digital realms where galaxies, dark matter, and light follow the rules of relativity to the letter. Take the Millennium simulation, one of the most ambitious virtual universes ever coded. Here, researchers recreated a cube of space over 2 billion light-years wide, populating it with trillions of particles representing dark matter halos, gas clouds, and fledgling galaxies. Then they hit play, watching as gravity sculpted this digital cosmos over 13 billion years of simulated time. But the real magic happens when they switch on the lensing effects. Suddenly, the simulation becomes a light-bending laboratory, where every warped galaxy arc, every ring, and every delayed supernova can be studied in perfect detail before astronomers even point their telescopes skyward. These simulations aren't just pretty animations, they're cosmic stones. When astronomers spot a lensed quasar split into 4 images or a galaxy stretched into a luminous arc, the first question is just, what are we seeing? It's which version of the universe explains this. By running thousands of variations, adjusting dark matters, tweaking galaxy cluster masses, even testing alternate theories of gravity, scientists can match virtual lensing patterns to real ones like a locksmith crafting keys. The Eagle project, for instance, simulated over 7,000 galaxies with such precision that their virtual lensing distortions mirrored actual observations down to the finest details. It's like having a universe in a box, where you can rewind, fast forward, and tweak the laws of physics to see what fits. But the true power of these simulations lies in their predictive muscle. Before the James Space Telescope launched, teams used simulations to forecast what lensed galaxies from the universe's first billion years might look like. They modeled how infant stars, ultraviolet light would stretch and brighten as it curved around foreground clusters, predicting the exact spectral signatures should hunt for. And when the telescope's first deep-field images revealed those very patterns, galaxies smeared into crimson arcs, their light amplified by spacetime's curvature, it wasn't just a triumph of observation. It was a validation of the digital universes that had rehearsed this moment for years. Upcoming sky surveys like the observatory's LSSD will take this synergy to new heights. Every night, it'll capture millions of lensing events, from fleeting flashes to subtle distortions in galaxy shapes. Without simulations, that avalanche of data would be overwhelming, a cosmic jigsaw with no reference image. But by pre-running scenarios where dark matter behaves differently or galaxies cluster in unexpected ways, astronomers can sift through the noise, spotting anomalies that might rewrite our understanding of gravity itself. What's astonishing is how these virtual realms blur the line between prediction and discovery. When the first dark galaxy was found, a clump of dark matter bending light with no visible stars, it wasn't luck. Simulations had already suggested such invisible structures should exist, lurking like cosmic ghosts. Now, as AI-powered simulations grow even more intricate, they're not just interpreting the universe's illusions, they're anticipating ones we haven't even spotted yet. So the next time you see a breathtaking image of a lensed galaxy, remember, somewhere in a supercomputer's memory, that exact cosmic mirage was rehearsed long before light ever reached our telescopes. We're standing at the edge of a revolution in how we see the universe, and it all hinges on bending light. Right now, telescopes have given us breathtaking glimpses of gravitational lensing's power, but they're just the opening act. The real show begins when observatories like the observatory swing into action, scanning the entire southern sky every few nights with a camera so massive it could capture a golf ball on the moon. This isn't just an upgrade, it's a transformation. Imagine spotting not just a handful of lensed galaxies, but millions, each one a cosmic detective story waiting to be decoded. Then there's Euclid, the European Space Agency's dark matter hunter, designed to map the invisible web of the cosmos with precision never before possible. While peers at tiny patches of sky like a jeweler examining gems, Euclid will take in vast swaths of space, measuring the subtlest distortions in billions of galaxies to trace dark matter's hidden fingerprints. Together, these projects will turn gravitational lensing from a rare curiosity into astronomy's workhorse, revealing everything from rogue planets drifting between stars to the universe's earliest galaxies, like fireflies caught in a spotlight. But here, the game changer, AI. Sifting through the avalanche of data from these telescopes would take humans centuries, but machine learning algorithms are already training on simulated universes to spot lensed objects in seconds. Some programs can even predict where new lenses should form, guiding telescopes to cosmic mirages before they've fully appeared. It's like having a treasure map where X marks the spot, except instead of gold, the prize might be a galaxy so ancient its light predates Earth itself. What's thrilling is how these tools will tackle cosmology's biggest puzzles. Take dark energy, the mysterious force accelerating the universe's expansion. By combining lensing maps from an Euclid, scientists will measure how dark energy's push has warped the cosmic web over billions of years, testing whether it's truly constant or changing over time. Others will hunt for primordial black holes, leftover relics from the Big Bang, by scanning for their telltale flickers in the data stream. And then there's the wild card, anomalies. Every time we've mapped the universe in new ways, we've stumbled onto the unexpected, like galaxies that rotate too fast or cosmic voids that defy gravity's rules. With lensing as our guide, who knows what surprises lie ahead? The next decade won't just add to our knowledge, it'll rewrite the playbook. Imagine a future where every high school astronomy class studies lensed supernovae-like, where telescopes ping our phones with real-time alerts about new rings forming, where dark matter's blueprint is as familiar as the periodic table. That's the golden age we're stepping into, one where spacetime's curves aren't just distortions, but the universe's way of whispering its secrets directly to us. And the best part, we're just starting to listen. What if the universe isn't the only one? The idea of parallel realities, other cosmic realms lurking just beyond our perception, has long been the stuff of science fiction. But here's the twist. Gravitational lensing might be the key to testing whether these alternate dimensions are more than just fantasy. It sounds like something straight out of a comic book, but some physicists suspect that if other universes exist, their gravity could subtly warp our own spacetime, leaving faint imprints in the way light bends around galaxies or distorts the cosmic microwave background. Think of it like a shadow passing behind a curtain. You might not see the source, but you can spot the ripple it leaves in the fabric. The math behind this is as mind-bending as the premise itself. In certain multiverse theories, like string theory's brane worlds, our universe could be a three-dimensional membrane floating in a higher dimensional space, with other branes, parallel universes, hovering just out of reach. If these branes wobble or brush against ours, their gravitational influence could nudge the path of light in ways that don't quite match predictions. Lensing becomes the ultimate detective tool, scanning for anomalies in galaxy clusters where the bending seems slightly off, or in the cosmic microwave background's polarization patterns, where unexplained swirls might betray a tug from another reality. One of the most tantalizing hints comes from the so-called cold spot in the cosmic microwave background, a patch of sky where temperatures dip strangely low. Some researchers argue it could be a bruise from a collision with another universe, its gravity subtly warping the light we observe. Others point to oddities in lensed quasar time delays, where light from the same object arrives at Earth with timing discrepancies that standard cosmology can't fully explain. Could these be echoes of invisible dimensions tugging at spacetime from the shadows? Of course, this is frontier science, speculative, controversial, and far from proven. Critics argue these anomalies could have mundane explanations, like statistical flukes or gaps in our understanding of dark matter. But that's the beauty of lensing. It doesn't just magnify distant galaxies, it amplifies our ability to ask wild questions. Future telescopes like the Observatory or CMB-S4 will map the cosmic microwave background with unprecedented precision, hunting for those telltale distortions that might whisper of other worlds. And if they find nothing, that's just as valuable. Science thrives on testing even the craziest ideas because every dead end still points us toward a deeper truth. So while we're not saying parallel universes are hiding in your backyard, we are saying the cosmos has a way of surprising us. From bending starlight to revealing dark matter, gravitational lensing has already rewritten the rules of reality. Who's to say it won't do it again? This time by cracking open a door to the multiverse. After all, the universe's greatest illusions often turn out to be its most revealing truths. Hollywood has a knack for turning mind-bending physics into blockbuster spectacle, and few cosmic phenomena dazzle on screen like gravitational lensing. Take Christopher's Interstellar, where the black hole gargantua looms over the story like a spinning, glowing whirlpool of doom. That wasn't just artistic flair, brought in physicist Kip to ensure the visuals matched real relativity. The result: a black hole so scientifically accurate its lensing effects, the warped starlight wrapping around its shadow, earned a published paper. The accretion disk's double image, curving above and below the hole like a halo, that's exactly how light would bend around a spinning singularity. For once, fiction didn't just borrow from science, it advanced it. But not every sci-fi story sticks to the textbook. In Star Trek, lensing often gets a dramatic upgrade, with black holes distorting starships like taffy or spitting them into alternate dimensions. Real lensing doesn't quite work that way. It's more about subtle shifts in light than cosmic teleportation. Yet these creative liberties reveal something deeper. Lensing isn't just a tool for astronomers. It's a narrative device, a way to visualize the unseen forces shaping the universe. When Event Horizon portrays a haunted ship emerging from a lensed mirage, or Contact uses warped spacetime to hint at alien engineering, they're tapping into the same awe that drives real astrophysics. Books push the boundaries even further. In The Three-Body Problem, an alien civilization uses lensing effects to magnify their star's flickers, sending coded messages across the cosmos. It's a brilliant twist, one that mirrors how real scientists study lensed quasars for clues about distant galaxies. Meanwhile, House of Suns imagines a future where entire civilizations orbit black holes, using their lensing effects as natural telescopes. The science might be speculative, but the core idea rings true. Gravity's ability to bend light isn't just a quirk of nature. It's a canvas for storytellers. What's fascinating is how these fictional takes loop back to inspire real science. After Interstellar, researchers used its black hole simulations to study how lensing could reveal the spin of real supermassive holes. Even Star Trek's wilder ideas, like using lensing to cloak objects, have sparked serious papers on whether gravity could ever manipulate light that way. The line between sci-fi and science blurs because both chase the same question: what happens when the rules of reality twist? So the next time you see a warped on screen, remember, you're not just watching special effects. You're seeing humanity's attempt to grapple with a universe where light doesn't play fair, where spacetime folds like origami, and where the strangest truths often outshine fiction. Whether it's Gargantua's haunting glow or a novelist's vision of lensed alien signals, these stories remind us that the cosmos's greatest magic trick, bending light itself, is real. And that's a plot twist worth savoring. You might think uncovering the universe's greatest illusions requires a D and access to $1 billion telescope. But here's the secret. Some of the most exciting lensing discoveries have come from everyday stargazers sitting at their laptops. Take the case of a bizarre green cosmic cloud spotted by Dutch schoolteacher Van while classifying galaxies online, or the amateur who noticed a faint arc in a public image, leading astronomers to confirm a new ring. These aren't flukes, they're proof that cosmic exploration has gone crowdsourced, and you could be the next to spot something revolutionary. Getting started is easier than you guess. Projects like Galaxy Zoo invite anyone with an internet connection to scan telescope images for telltale lensing signatures, stretched galaxies, duplicated quasars, or strange blue smears that might be distant objects by unseen mass. The training takes minutes. You'll learn to distinguish lensed arcs from spiral arms or camera artifacts, then dive into real data from observatories like PAN-SDARRS or the Dark Energy Survey. What feels like a cosmic treasure hunt is actually vital science. Each classification helps narrow millions of candidates down to a handful worth professional study. For those who love numbers, platforms like Space Warps offer deeper dives. Here, you'll analyze light curves from quasars, watching for the subtle brightening that signals an event, perhaps a rogue planet drifting silently between us and the star. There's even a chat feature where volunteers compare notes, turning cosmic detective work into a social experience. One dedicated amateur recently flagged a quasar flickering oddly in decade-old data. It turned out to be a rare double lens system, with two galaxies warping the light at different distances. The thrill isn't just in the hunt, it's in the real-world impact. When the Frontier Fields project released its deep field images, citizen scientists found lensed galaxies pros had overlooked, some so dramatically their individual star clusters were visible. Others have spotted failed lenses places where theory predicted warping, but none appeared, hinting at gaps in our dark matter maps. These contributions aren't footnotes. They're published in journals alongside professional findings, with volunteers often listed as co-authors. What's truly game-changing is how tech is leveling the playing field. Free tools like Light let you overlay lensing probability maps on telescope images, while apps like Gravity Spy train AI using amateur classifications to spot new events faster. There's even a Twitter bot at LensBot that alerts followers to fresh lensing candidates needing review. The barrier to entry has never been lower. Whether you're a student on a tablet or a retiree with a home telescope, the cosmos is waiting for your perspective. So here's the challenge. Next time you scroll past a stunning space photo online, pause, zoom in. That faint streak or odd symmetry might not be noise. It could be light bent across billions of years, visible to anyone curious enough to look. The universe's greatest magic trick isn't reserved for those with fancy titles or giant observatories. Sometimes, all it takes is a sharp eye, a little patience, and the courage to wonder, what if that's not supposed to look like that? After all, the next cosmic illusion waiting to be unmasked might just have your name on it. The Nobel Prize isn't just a gold medal and a handshake from the Swedish king. It's a spotlight on ideas that reshape how we see the universe. In 2011, that spotlight landed on 3 astronomers who made a discovery so shocking it upended cosmology. The universe isn't just expanding, it's accelerating. They're key evidence. Distant supernovae, acting as cosmic mileposts that revealed space itself, was stretching faster over time. But here's what rarely makes the headlines. Gravitational lensing was the silent partner in this revolutionary finding, sharpening the measurements and ruling out doubts like a cosmic fact-checker. When Saul and Adam measured those supernovae, they faced a puzzle. To prove the universe's expansion was speeding up, they needed pristine distance measurements, no blurry data, no ambiguous gaps. That's where lensing stepped in. By studying how foreground galaxies warped the light of these exploding stars, astronomers could account for distortions that might otherwise skew the results. Some supernovae even appeared brighter than expected, their light amplified by unseen clumps of dark matter along the line of sight. A boost that, once corrected, tightened the acceleration signal like a tuning fork. But lensing's role didn't stop there. As the Nobel-winning discovery rippled through physics, skeptics wondered, could dust or evolving supernovae mimic cosmic acceleration? Lensing provided the knockout punch. Surveys like the Canada-France-Hawaii Telescope Legacy study mapped millions of galaxies, using weak lensing to trace how dark matter's gravitational scaffolding had grown sparser over billions of years. Exactly what you'd expect if dark energy was stretching space apart. The cosmic microwave background, imprinted with lensing patterns from the early universe, independently confirmed the acceleration. Together, these lines of evidence formed an ironclad case, with lensing as the thread stitching them together. What's thrilling is how lensing continues to test the limits of this discovery. Alternative theories, like modified gravity or phantom energy, predict subtle differences in how lensing distortions should evolve across cosmic time. Projects like the Dark Energy Survey are chasing these nuances, measuring the shapes of 100 million galaxies to see if dark energy's push has changed over the eons. Even time-delayed lensed supernovae are joining the hunt, their staggered arrivals offering a stopwatch for the universe's expansion rate. The takeaway, that Nobel Prize wasn't just about supernovae. It was a triumph of cross-examining the cosmos with every tool available, and gravitational lensing proved to be one of the most reliable witnesses. As we peer deeper into the dark energy puzzle, lensing remains the ultimate arbiter, quietly separating cosmic fact from fiction while the universe keeps racing outward, faster than we ever dreamed. Gravitational lensing may be one of our most powerful cosmic tools, but even this celestial magnifying glass has its limitations. For starters, nature doesn't always cooperate with perfect alignments. To create those stunning rings or multiple images of a single quasar, the distant light source, the massive lensing object, and Earth all need to line up with near mathematical precision. It's like trying to thread a needle from across a football field, except the needle is a galaxy cluster billions of light years away, and the thread is a beam of light that's been traveling since before Earth existed. Most of the time, the angles are just slightly off, leaving astronomers with faint, distorted arcs instead of textbook-perfect rings. Even when we do spot a lensed object, there's no guarantee we'll see it again. Some lensing events, especially flashes, vanish within days, leaving behind more questions than answers. Then there's the issue of resolution. While lensing can magnify distant galaxies, it doesn't sharpen them like a telescope's optics. Imagine using a funhouse mirror to read fine print. The text might get bigger, but it's also stretched and blurred. That's why some of the most distant lensed galaxies, though amplified, still appear as smudges. We know they're ancient star factories, but their finer details, individual star clusters or nascent planets, remain tantalizingly out of focus. And while lensing reveals the gravitational fingerprints of dark matter, it can't tell us what that matter is, only where it's hiding. Perhaps the biggest blind spot is what lensing doesn't show us, the interiors of the very objects doing the lensing. A galaxy cluster might bend light spectacularly, but that tells us nothing about the black holes churning at its heart or the exotic physics playing out in its densest regions. It's like studying a magnifying glass by the shadows it casts, never seeing the glass itself. But astronomers are far from helpless. When lensing hits its limits, other tools step in. Spectroscopy dissects the light from lensed objects, revealing their composition, temperature, and motion. Radio telescopes peer through cosmic dust that optical lenses can't penetrate. And by combining lensing with gravitational wave detectors, scientists are beginning to hear the collisions of massive objects while simultaneously watching their lensed aftermath. Even relativity's greatest trick has its constraints, but that's the beauty of science. By stacking one method atop another, we turn partial glimpses into a fuller portrait. Lensing might not solve every cosmic riddle alone, but in the orchestra of astronomy, it's the instrument that plays the notes others can't reach. Peering into the atmosphere of a planet light years away sounds like science fiction, but gravitational lensing is turning this fantasy into reality. Hear how it works. When a distant star and its exoplanet align perfectly with a foreground object, like a black hole or dense galaxy cluster, the planet's atmosphere doesn't just get, its light gets stretched into a spectrum, a rainbow-like fingerprint of its chemical makeup. Normally, these worlds are just dim specks lost in their star's glare. But under the cosmic magnifying glass of lensing, even a tiny Earth-like exoplanet can reveal whether its skies hold water vapor, methane, or even the telltale oxygen of a living world. Take the case of a gas giant dubbed Lensed 1, spotted when its host star passed behind a massive galaxy. As the star's light bent around the galaxy's gravity well, its planet's atmosphere absorbed specific wavelengths, leaving dark lines in the spectrum like a barcode. Astronomers decoded those lines to find sodium, potassium, and most intriguingly, water clouds swirling in its upper layers. Without lensing, this world would have been invisible. Now it's a case study in how alien weather systems work. The real prize, though, is finding biosignatures, chemical combinations that hint at life. On Earth, Oxygen and methane coexist in our atmosphere only because plants and microbes constantly replenish them. Spotting that duo on a lensed exoplanet would set off fireworks in the scientific community. Projects like NASA's upcoming Nancy Grace Roman telescope are designed to catch these moments, scanning for the fleeting lensing events that might amplify an Earth twin's atmosphere just long enough to sniff out its secrets. But there's a catch. These alignments are vanishingly rare. A star and its planet must pass almost exactly behind a massive lens, and the event might last mere hours. That's where AI steps in. Algorithms now scour sky surveys in real time, flagging suspicious brightening patterns that could signal a lensing exoplanet in progress. When they spot a candidate, telescopes worldwide swivel into action, capturing spectra before the cosmic window slams shut. What's astonishing is how much we can learn from so little light. In 2023, researchers used lensing to study a super-Earth's atmosphere over 30 light-years away. The data revealed not just molecules but wind patterns, a global jet stream racing at thousands of miles per hour. It's like deducing a hurricane's speed from the shadow it casts on a distant wall. The future holds even wilder possibilities. Imagine lensing magnifying a habitable zone exoplanet, reflected light, revealing continents and oceans, or spotting industrial pollutants in an alien sky techno-signatures of a civilization harnessing its planet's resources. Gravitational lensing doesn't just bend light, it bends the limits of what we thought possible, turning the universe's most massive objects into telescopes that bring alien worlds within reach. And somewhere out there, the right alignment might already be lining up, waiting to show us we're not alone. At the edge of a black hole where gravity crushes matter into oblivion and spacetime itself frays at the seams, this relativity faces its ultimate test. Here, in this realm of unimaginable density, quantum mechanics and gravity collide, and the distortions we see in gravitationally lensed light could be our first glimpse of the new physics hiding in the wreckage. For decades, relativity has predicted exactly how light should bend around black holes, but quantum theory whispers that spacetime might not be smooth and continuous as imagined. Instead, it could be pixelated, a seething foam of vanishingly tiny loops or strings where the rules we know break down. And if that's true, the lensed starlight wrapping around a black hole's shadow might carry subtle fingerprints of this quantum chaos. One leading contender, loop quantum gravity, suggests spacetime is woven from interlocking loops so small that a billion could fit in a single atom. Near a black hole's crushing grip, these loops might stretch or not, altering how spacetime warps light in ways relativity can't explain. Imagine throwing a ball through a waterfall. Classical physics predicts its arc, but if the water's flow is turbulent with unseen whirlpools, the ball might swerve unexpectedly. Similarly, if lensed starlight around a black hole deviates even slightly from predictions, say, with extra flickers or an asymmetrical glow, it could signal spacetime's granular quantum structure. The Event Horizon Telescope, which captured the first black hole image, is already hunting for these anomalies. Its next target, Sagittarius A star at our galaxy's center, might hold the clues. If the lensed ring of light around it shows faint fractal patterns or brightness variations that defy relativity's equations, it could hint at quantum gravity's influence. Some theorists even propose that certain lensing anomalies, like light appearing to stutter as it skirts a black hole's edge, might betray spacetime's discrete nature, like a film reel revealing its individual frames when played too slowly. But the stakes are higher than just tweaking equations. If relativity fails near black holes, it wouldn't mean was wrong, just incomplete like Newton before him. Every scientific revolution begins at the edges of what we know, and lensing offers a rare bridge between the cosmic and the quantum. Future telescopes like the planned Black Hole Cam Space Array will scrutinize lensed light with even finer precision, searching for deviations smaller than a proton's width. Whether they confirm enduring vision or unveil a wilder reality, one thing's certain. The universe's most extreme lenses, black holes, won't just bend light. They'll bend our understanding of reality itself. The cosmic microwave background isn't just a snapshot of the universe's infancy. It's a canvas where gravity has left its fingerprints in the faintest of brushstrokes. This ancient light, traveling for over 13 billion years, didn't make it to us unscathed. Along the way, it passed through galaxies, dark matter halos, and vast cosmic voids, each one bending its path like a whisper distorted through a maze of doors. The result? A pattern of subtle distortions in the CMB's temperature and polarization, a ghostly imprint of all the matter it encountered. Think of it as the universe's way of scribbling footnotes in the margins of its oldest manuscript, and gravitational lensing is the decoder ring that lets us read them. When the satellite mapped these distortions with unprecedented precision, it didn't just catalog the CMB's wrinkles, it weighed the unseen. Take neutrinos, those elusive particles that barely interact with matter. Normally, they're nearly impossible to pin down, but Lensing's fingerprints in the CMB revealed their collective mass. How? Because neutrinos, though tiny, are so abundant that their gravity subtly alters how the CMB's light bends across cosmic distances. Data showed these particles can't be more than a fraction of an proof that the universe's particles still leave a gravitational paper trail. Dark matter secrets are etched even deeper into these lensing patterns. The CMB's light didn't just bend around galaxies we can see, it curved around the invisible scaffolding between them, tracing dark matter's hidden web. Maps revealed how this mysterious substance clumps and stretches, confirming it makes up roughly 27% of the cosmos. But the real surprise came when scientists compared these lensing distortions to simulations. Some regions showed more warping than expected, hinting that dark matter might interact with itself in ways we've yet to understand, perhaps through unknown forces or particles beyond our current models. What's astonishing is how lensing turns the CMB from a static image into a dynamic record. Those faint smudges and swirls aren't just noise, they're a timeline of the universe's growth. By analyzing how lensing patterns evolve across different epochs, cosmologists can track how dark energy's push has countered gravity, pull over billions of years. It's like watching a sped-up film of the cosmos's expansion, with each frame written in bent light. And then there are the anomalies, places where the CMB's lensing doesn't quite match predictions. One patch of sky, dubbed the cold spot, shows less lensing than it should, as if a vast cosmic void sits between us and the early universe. Could this be evidence of a collision with another bubble universe, or just a statistical fluke? The debate rages, but the fact that we can even ask these questions speaks to lensing's power. The CMB was already our most powerful window into the Big Bang. Now, thanks to the way gravity sculpts its light, it's also a treasure map to everything that came after, written in distortions only the universe itself could have authored. Lens a galaxy cluster, and you're not just seeing a pretty cosmic mirage, you're stepping onto the universe's most honest scale. Here's the staggering truth. When astronomers measure how much a cluster bends the light of galaxies behind it, they're not just observing an illusion. They're taking its weight down to the last solar mass. The math is elegant in its simplicity. The more a cluster distorts light, the more massive it must be. But here's the shocker. When you tally up all the visible stars and gas in these clusters, the numbers never add up. They're laughably light, like weighing an elephant and getting the mass of a house cat. That discrepancy isn't an error, it's the signature of dark matter, the universe's hidden bulk. Take the Bullet Cluster, one of the most revealing weigh-ins in cosmic history. When these two galaxy clusters collided at millions of miles per hour, their visible gas, hot and glowing, slammed together and stalled at the collision site. But the lensing maps told a different story. The gravity-bending light from background galaxies wasn't centered on that gas. Instead, it traced two distinct blobs racing ahead, nearly untouched. That could only mean one thing. Most of the cluster's mass was invisible, sailing right through the wreckage like a ghost train. Those blobs, they were dark matter, outweighing the visible material 5-1. It was as if the universe handed us an X-ray revealing its hidden skeleton. But lensing doesn't just weigh clusters, it exposes the cosmic ledger where ordinary matter barely registers. In the Coma cluster, for instance, lensing measurements show a mass equivalent to 20 trillion suns. Strip away the dark matter and the stars and gas account for less than 10% of that. This isn't a fluke, it's the rule. Across the universe, from sprawling superclusters to humble galaxy groups, lensing consistently reveals that what shines is just the frosting on an invisible cake. The real power of this cosmic scale lies in its impartiality. Other methods of weighing galaxies, like tracking how fast stars orbit their centers, depend on assumptions about motion and gravity. Lensing cuts through the guesswork. It measures mass purely through spacetime's curvature, no matter if that mass emits light, absorbs it, or ignores it entirely. That's how we've mapped dark matter's tendrils stretching between galaxies, or spotted dark galaxies with hardly any stars at all. What's revolutionary is how this technique scales up. By combining millions of weak lensing measurements from surveys like the Dark Energy Survey, astronomers have constructed three-dimensional maps of the universe's mass distribution, a cosmic scaffolding where luminous galaxies are mere ornaments hanging from dark matter's invisible threads. These maps don't just show where mass is. They reveal how it's evolved over billions of years, tracing the gravitational tug-of-war between dark matter's pull and dark energy's push. Here's the humbling part. Without lensing, we might still be mistaking the universe's visible crumbs for the whole loaf. Every warped galaxy, every stretched arc of light is a reminder that the cosmos keeps its deepest secrets in the dark. And thanks to this relentless cosmic scale, we're finally learning to weigh what we cannot see. The elegant equations behind gravitational lensing prove that the universe's greatest magic tricks run on mathematics. At its core, the phenomenon boils down to deflection angle formula, a deceptively simple equation that predicts exactly how much light will bend around a massive object. Picture a beam of starlight grazing the sun. According to the formula, the light's path will curve by just 1.75, a tiny shift, but enough to make distant stars appear slightly out of place during an eclipse. That number isn't arbitrary. It's derived from fundamental constants like the speed of light and the gravitational constant, woven together by relativity's unshakable logic. But how does this translate to those dramatic rings and galaxy arcs we see in telescope images? Enter the lens equation, the workhorse of gravitational lensing calculations. Think of it like the recipe for a cosmic mirage. It takes three ingredients: the distance from Earth to the lensing object, the distance from the lens to the background light source, and the mass of the lens itself. Mix them together, and out pops a prediction for where and how the distorted images will appear. It's why astronomers knew exactly when to expect that delayed fifth image of supernova. The math had already mapped spacetime's curves like a subway planner drafting routes through a city. To grasp why light bends this way, imagine diving into a swimming pool. As sunlight enters the water, it slows down and changes direction, a familiar effect called refraction. Gravity warps light similarly, but instead of water molecules causing the slowdown, it's the sheer weight of mass denting spacetime itself. The denser the object, the steeper the dent, and the sharper the light's curve. A galaxy cluster's immense gravity creates such a profound dip that light can loop around it like a marble spiraling around a funnel's edge, creating those mesmerizing rings and arcs. What's astonishing is how these abstract symbols on a page translate to real cosmic spectacles. Take the famous cross, 4 identical quasar images arranged in a perfect square around a foreground galaxy. The lens equation didn't just predict this could happen, It told astronomers exactly how the image's brightness and spacing would reveal the galaxy's hidden dark matter halo. When telescopes confirmed these predictions down to the percentage point, it wasn't just a victory for relativity. It was proof that mathematics is the universe's native language. For those who love numbers, the real magic lies in the subtleties. Tiny discrepancies between lensing observations and equations can unveil revolutionary physics. Some galaxy clusters bend light slightly more than their visible mass should allow, hinting at exotic dark matter behaviors. Others show anomalies in how images are distorted, sparking debates about whether constants need tweaking for extreme scales. Every decimal place in these calculations isn't just academic, it's a potential doorway to new cosmic truths. So the next time you see an image of a lensed galaxy, remember, those elegant arcs aren't accidents. They're the universe solving an intricate geometry problem in real time, with gravity as its compass and light as its pencil. And thanks to mathematics, we're not just witnessing the show, we've cracked the code to read the script. Wormholes have long been the stuff of science fiction, cosmic shortcuts where a spaceship might leap across the galaxy in an instant. But what if these spacetime tunnels aren't just fantasy? Gravitational lensing might hold the key to spotting them, not with warp drives or glowing portals, but through subtle distortions in the light bending around their hypothetical mouths. Picture this: a distant star's light passes near where a wormhole might lurk, and instead of a single image, we see two. One from light curving around the left side of the wormhole's entrance, another from the right. These wouldn't be ordinary doubles like lensed quasars. The images might differ in brightness or even color, as light taking different paths through a wormhole's twisted spacetime could emerge stretched or compressed, like echoes warped by a funhouse mirror. The math behind this is as mesmerizing as the idea itself. In theory, a traversable wormhole, unlike a black hole, wouldn't have an event horizon to swallow light forever. Instead, its throat might act like a lens, bending light without trapping it. Some models predict a distinct ring of light around a wormhole's shadow, similar to a black hole's photon ring, but with a telltale asymmetry. Light passing through the wormhole's throat could emerge with creating a spectral fingerprint unlike anything produced by ordinary lensing. Even stranger, certain wormhole configurations might split light into multiple beams, each arriving at Earth at slightly different times, like a cosmic SOS signal scrambled by spacetime's folds. Of course, no confirmed wormhole has ever been spotted, but lensing offers a way to hunt for them without needing to dive into the abyss. Astronomers could scan the skies for anomalous lensing events, places where the bending of light defies the predictions of equations when applied to ordinary matter. Imagine finding a galaxy cluster that lenses background light too much, as if hidden mass lurks where none is visible. Most would blame dark matter, but what if the excess distortion comes from a wormhole's gravity, its entrance hidden in plain sight? Or consider a star that flickers in a way no event can explain, its light dimming and brightening as if something unseen and tunnel-shaped drifts between us and it. The wildest possibility: wormholes might not even need exotic matter to stay open. Recent theories suggest certain quantum geometries or higher dimensional physics could stabilize them naturally, leaving lensing as our only way to detect their presence. Projects like the observatory, which will image the entire southern sky every few nights, could stumble upon these anomalies by accident, flagging weird lensing patterns that don't fit the cosmic mold. For now, wormholes remain in the realm of theory, but so did black holes once, and gravitational waves and dark energy. The universe has a habit of taking our wildest ideas and revealing they've been true all along. If wormholes are out there, lensing won't just find them. It'll rewrite the rules of spacetime, proving that the universe's greatest shortcuts were hiding in the warped light all along. Until then, every strange lensing anomaly is a breadcrumb, one that might lead us to the cosmos' most elusive doors. Lensing doesn't just bend the light our eyes can see, it twists the entire electromagnetic spectrum, revealing hidden layers of the cosmos depending on how we choose to look. Take radio waves, for instance. While optical telescopes show us the graceful arcs of lensed galaxies, radio arrays like ALMA pierce through the cosmic dust that obscures their star-forming hearts. In 2017, ALMA spotted a lensed galaxy so dusty it was practically invisible too. But in radio wavelengths, its light shone through, exposing a frenzy of stellar nurseries churning out new stars 1,000 times faster than the Milky Way. The kicker: the lensing effect amplified the galaxy's radio glow 32 times, gifting astronomers a crystal-clear view of chemistry in action. Carbon monoxide molecules swirling in vast clouds, the raw material for future planets. X-ray lenses paint an even fiercer picture. When trains its gaze on a galaxy cluster acting as a lens, it doesn't just see the objects behind it, it maps the scorching plasma within the cluster itself. This million-degree gas, too hot to emit visible light, glows brightly in X-rays, revealing how the cluster's gravity distorts not just light, but the very fabric of its environment. Some clusters, like 2163, show X-ray jets from supermassive black holes bent into bizarre curves by the cluster's gravity, like cosmic fountains twisted by an unseen hand. These distortions aren't just eye candy. They let scientists weigh the cluster's total mass, including the dark matter lurking between the glowing gas clouds. Infrared lenses, meanwhile, peer through cosmic time. The James Space Telescope's infrared vision combines with lensing to spotlight galaxies so ancient their light has stretched into infrared wavelengths from the universe's expansion. In its first deep-field image, a lensed galaxy dubbed the Sparkler appeared not as a single smudge but as multiple ruby-red dots, each a duplicate image by a foreground cluster. But here's the twist: those dots weren't stars. They were globular clusters, relics from the universe's first 2 billion years, whose faint glow would have been lost without both infrared sensitivity and lensing's amplification. The real power comes when these wavelengths team up. A single lensed galaxy might reveal its stars in visible light, its dust in radio, and its black hole's fury in X-rays. A multi-wavelength dissection that would be impossible without gravity's magnifying effect. Even gamma rays, the universe's most energetic light, can be lensed. In 2014, the Fermi telescope detected gamma-ray photons from a distant blazar arriving minutes apart, their paths bent differently by an intervening galaxy. That delay, measured in the highest energy light possible, became a stress test for relativity itself. What's clear is this: the universe's grand illusions don't play favorites with wavelength. Whether it's radio whispers from stellar nurseries, X-ray screams from black holes, or infrared echoes from the cosmic dawn, lensing ensures we're not just seeing the cosmos, we're seeing it in every possible light. And with each new spectrum we unlock, gravity's funhouse mirror reflects back another piece of the puzzle. The Nobel Prize isn't just a gold medal and a handshake from the Swedish king. It's a spotlight on ideas that reshape how we see the universe. In 2011, that spotlight landed on 3 astronomers who made a discovery so shocking it upended cosmology. The universe isn't just expanding, it's accelerating. Their key evidence: distant supernovae, acting as cosmic mileposts that revealed space itself was stretching faster over time. But here's what rarely makes the headlines. Gravitational lensing was the silent partner in this revolutionary finding, sharpening the measurements and ruling out doubts like a cosmic fact-checker. When Saul and Adam measured those supernovae, they faced a puzzle. To prove the universe's expansion was speeding up, they needed pristine distance measurements, no blurry data, no ambiguous gaps. That's where lensing stepped in. By studying how foreground galaxies warped the light of these exploding stars, astronomers could account for distortions that might otherwise skew the results. Some supernovae even appeared brighter than expected, their light amplified by unseen clumps of dark matter along the line of sight. A boost that, once corrected, tightened the acceleration signal like a tuning fork. But Lensing's role didn't stop there. As the Nobel-winning discovery rippled through physics, skeptics wondered, could dust or evolving supernovae mimic cosmic acceleration? Lensing provided the knockout punch. Surveys like the Canada-France-Hawaii Telescope Legacy study mapped millions of galaxies, using weak lensing to trace how dark matter's gravitational scaffolding had grown sparser over billions of years. Exactly what you'd expect if dark energy was stretching space apart. The cosmic microwave background, imprinted with lensing patterns from the early universe, independently confirmed the acceleration. Together, these lines of evidence formed an ironclad case, with lensing as the thread stitching them together. What's thrilling is how lensing continues to test the limits of this discovery. Alternative theories, like modified gravity or phantom energy, predict subtle differences in how lensing distortions should evolve across cosmic time. Projects like the Dark Energy Survey are chasing these nuances, measuring the shapes of 100 million galaxies to see if dark energy's push has changed over the eons. Even time-delayed lensed supernovae are joining the hunt, their staggered arrivals offering a stopwatch for the universe's expansion rate. The takeaway, that Nobel Prize wasn't just about supernovae. It was a triumph of cross-examining the cosmos with every tool available, and gravitational lensing proved to be one of the most reliable witnesses. As we peer deeper into the dark energy puzzle, lensing remains the ultimate arbiter, quietly separating cosmic fact from fiction while the universe keeps racing outward, faster than we ever dreamed. Gravitational lensing may be one of our most powerful cosmic tools, but even this celestial magnifying glass has its limitations. For starters, nature doesn't always cooperate with perfect alignments. To create those stunning rings or multiple images of a single quasar, the distant light source, the massive lensing object, and Earth all need to line up with near mathematical precision. It's like trying to thread a needle from across a football field, except the needle is a galaxy cluster billions of light years away, and the thread is a beam of light that's been traveling since before Earth existed. Most of the time, the angles are just slightly off, leaving astronomers with faint, distorted arcs instead of textbook-perfect rings. Even when we do spot a lensed object, there's no guarantee we'll see it again. Some lensing events, especially flashes, vanish within days, leaving behind more questions than answers. Then there's the issue of resolution. While lensing can magnify distant galaxies, it doesn't sharpen them like a telescope's optics. Imagine using a funhouse mirror to read fine print. The text might get bigger, but it's also stretched and blurred. That's why some of the most distant lensed galaxies, though amplified, still appear as smudges. We know they're ancient star factories, but their finer details, individual star clusters or nascent planets, remain tantalizingly out of focus. And while lensing reveals the gravitational fingerprints of dark matter, it can't tell us what that matter is, only where it's hiding. Perhaps the biggest blind spot is what lensing doesn't show us, the interiors of the very objects doing the lensing. A galaxy cluster might bend light spectacularly, but that tells us nothing about the black holes churning at its heart or the exotic physics playing out in its densest regions. It's like studying a magnifying glass by the shadows it casts, never seeing the glass itself. But astronomers are far from helpless. When lensing hits its limits, other tools step in. Spectroscopy dissects the light from lensed objects, revealing their composition, temperature, and motion. Radio telescopes peer through cosmic dust that optical lenses can't penetrate. And by combining lensing with gravitational wave detectors, scientists are beginning to hear the collisions of massive objects while simultaneously watching their lensed aftermath. Even relativity's greatest trick has its constraints, but that's the beauty of science. By stacking one method atop another, we turn partial glimpses into a fuller portrait. Lensing might not solve every cosmic riddle alone, but in the orchestra of astronomy, it's the instrument that plays the notes others can't reach. Imagine a world where we could study the air of a planet trillions of miles away, not by sending probes, but by turning the universe itself into the ultimate telescope. That's the promise of gravitational lensing when it comes to exoplanet atmospheres. Normally, the light from a distant planet is drowned out by the glare of its host star, like trying to spot a firefly next to a spotlight. But when a massive object like a galaxy cluster bends and amplifies that star's light, the planets orbiting it get too, and with them, the faint chemical fingerprints in their atmospheres. This isn't just theory. In 2023, researchers used this very technique to analyze the atmosphere of a super-Earth 30 light-years away. As the planet's host star passed behind a foreground galaxy, its light, and the starlight filtering through the planet's atmosphere was stretched into a spectrum. Hidden in that rainbow of light were dark absorption lines, like barcodes revealing the presence of water vapor, sodium, and even swirling clouds of silicate particles. Without lensing, this world would have been a featureless dot. Instead, it became a case study in alien weather. The real prize, though, is the hunt for biosignatures, chemical combinations that could hint at life. On Earth, oxygen and methane coexist in our atmosphere only because plants and microbes constantly replenish them. Spotting that duo on a lensed exoplanet would send shockwaves through the scientific community. The challenge: these alignments are cosmic lightning strikes. A star and its planet must pass almost perfectly behind a massive lens, and the event might last mere hours. But when it happens, the payoff is extraordinary. Here, where cutting-edge technology steps in. AI algorithms now scan sky surveys in real time, flagging stars that brighten in ways suggesting a lensing event in progress. When one triggers, telescopes worldwide swivel into action, capturing spectra before the cosmic window slams shut. Projects like NASA's upcoming Nancy Grace Roman Telescope are designed explicitly for this hunt, monitoring millions of stars for the telltale flickers of lensed exoplanets. What's astonishing is the level of detail we can extract from so little light. In one study, lensing revealed not just molecules in an exoplanet's atmosphere, but wind patterns, a global jet stream racing at thousands of miles per hour. It's like deducing a hurricane's speed from the shadow it casts on a distant wall. Future observations might even spot the reflective glint of oceans or continents on habitable zone worlds, or the artificial glow of city lights, technosignatures of a civilization harnessing its planet's night. The implications are staggering. While traditional methods like transit spectroscopy are limited to nearby stars, lensing can profile planets orbiting stars halfway across the universe. It's our only shot at studying atmospheres in galaxies beyond the Milky Way, should the right alignment occur. And somewhere out there, the perfect cosmic coincidence might already be lining up. A habitable world's light bent, and just enough for us to glimpse the chemistry of an alien biosphere. In the grand search for life beyond Earth, gravitational lensing isn't just a tool. It's the universe conspiring to show us its most guarded secrets. At the very edge of a black hole's crushing grip, where gravity warps spacetime beyond recognition, its theory of relativity faces its ultimate test, and gravitational lensing might be the only witness. This isn't just about light bending around massive objects anymore. It's about peering into the chaotic frontier where relativity and quantum mechanics collide. Imagine spacetime not as a smooth fabric, but as a seething quantum foam, a turbulent sea of unimaginably tiny loops or strings vibrating at the smallest scales. Here, the orderly equations of general relativity might fray at the edges, and the way light bends around black holes could betray these hidden fractures in reality itself. One of the boldest contenders in this cosmic courtroom is loop quantum gravity, a theory suggesting spacetime is woven from interlocking loops a billion times smaller than an atom. Near a black hole's event horizon, these loops might stretch or knot in ways that alter how light curves through space, creating subtle but measurable deviations from predictions. It's like throwing a ball through a waterfall. Classical physics predicts its arc, but if unseen whirlpools churn beneath the surface, the ball might swerve unexpectedly. Similarly, if lensed starlight around a black hole flickers asymmetrically or forms irregular rings, it could signal spacetime's granular quantum structure poking through. The Event Horizon Telescope, famous for capturing the first black hole image, is already hunting for these anomalies. Its next target, Sagittarius A*, the supermassive black hole at our galaxy's center, could be the stone for quantum gravity. If the lensed ring of light around its shadow shows faint fractal patterns or brightness variations that defy relativity's clean equations, it might reveal spacetime's hidden quantum scaffolding. Some theorists even suggest that light skirting a black hole's edge could appear to stutter, its path jittering as it interacts with discrete spacetime grains, like a film reel revealing its individual frames when slowed down enough. But loop quantum gravity isn't the only theory in the running. String theory proposes that fundamental particles aren't points but vibrating strings, and their interactions could warp spacetime in ways that imprint on lensing patterns. Certain models predict extra dimensions curled up at microscopic scales, dimensions whose gravitational influence might subtly distort how black holes bend light. Then there's holographic principle, suggesting that all the information in a volume of space might be encoded on its boundary, a radical idea that could manifest in lensed light-carrying echoes of information from the black hole's hidden surface. The stakes couldn't be higher. If relativity holds firm even in these extreme conditions, it cements legacy as the unparalleled architect of cosmic order. But if lensing reveals cracks in the foundation, say light bending slightly less or more than expected, it could mark the dawn of a new physics, one that bridges the quantum and cosmic realms. Future observatories like the planned Black Hole Cam Space Array or the Next Generation Event Horizon Telescope will scrutinize these lensing effects with nanometer precision, turning black holes into laboratories for probing reality's deepest laws. What's thrilling is that we don't need to invent new tools to test these wild ideas. The universe has already built the perfect experiment: black holes, nature's most ruthless warpers of light. Every photon that grazes their edges carries a coded message about spacetime's true nature. If we can just decipher the bends, the delays, the flickers hidden in their twisted paths. Whether confirming vision or unveiling a stranger reality, gravitational lensing remains the ultimate translator, turning the silent distortions of light into a manifesto for the cosmos's next great revolution. The cosmic microwave background isn't just a static snapshot of the universe's fiery birth. It's a living document, its ancient light etched with the gravitational fingerprints of everything it encountered on its 13 billion-year journey to us. When the satellite mapped this primordial glow with microscopic precision, it didn't just capture temperature variations from the Big Bang. It revealed something far subtler, the faint warping of that light by the universe's hidden scaffolding. Every galaxy cluster, every tendril of dark matter the CMB's photons grazed on their epic voyage left a barely perceptible curl in their paths, like invisible hands gently bending the pages of a cosmic manuscript. These distortions are more than cosmic graffiti, they're a forensic tool. Take neutrinos, those ghostly particles that stream through matter almost unnoticed. Their combined gravity is so feeble that detecting their mass seemed impossible until analyzed the CMB's lensing patterns. The way these patterns subtly deviate from expectations revealed that neutrinos can't weigh more than a fraction of an. It's as if the universe hid its particles in plain sight, their presence betrayed only by how they nudged spacetime's fabric over eons. Dark matter's secrets are written even deeper into these lensed whispers. While the CMB's temperature spots tell us about the early universe's lumpiness, its lensing distortions map how that lumpiness evolved, how dark matter's invisible web grew denser in some regions and stretched thin in others. Data showed this web accounts for 27% of the cosmos's mass energy, but with a twist. Some areas warped the CMB more than simulations predicted, as if dark matter's gravity played by slightly different rules in the universe's emptiest voids. Could this hint at dark matter interacting with itself, or perhaps an unseen force tugging at the cosmic web? The lensed CMB doesn't answer yet, but it's asking the right questions. What's astonishing is how these imprints turn the CMB into a time machine. By separating lensing effects from the primordial signal, cosmologists can reconstruct how dark matter's distribution changed across cosmic epochs, like flipping through frames of a movie showing the universe's growth. This revealed dark energy's fingerprints too, the accelerated stretching of space that made matter's clumping slow down over time. The CMB's lensing patterns are the only direct record of this tug-of-war, a billion-year chronicle of gravity's struggle against dark energy's push. Then there are the anomalies, places where the CMB's lensing doesn't just deviate but defies. The infamous cold spot, a patch of sky where temperatures dip strangely low, shows weaker lensing than it should, as if a vast cosmic void lies between us and the early universe. Some theorists whisper this could be a bruise from a collision with another universe's bubble, its gravity subtly altering how the CMB's light curved through spacetime. Others argue it's just a statistical fluke, but the fact that we can debate it at all shows lensing's power to turn the CMB from a relic into a detective. This is the magic of reading the universe's palimpsest. The CMB's surface tells the story of the Big Bang's aftermath, but its lensing distortions are marginalia scribbled by everything that came after: galaxies, black holes, dark matter's unseen architecture. Its data was just the first draft. Upcoming observatories like the Array will scan these patterns with even finer precision, hunting for clues about inflation's quantum seeds or the nature of dark energy. Every new layer we decode doesn't just refine our origin story. It reminds us that the universe's oldest light is still telling new tales. Imagine stepping onto a cosmic scale that doesn't measure pounds or kilograms, but the collective weight of entire galaxies, black holes, and the invisible glue holding them together. That's the revolutionary power of gravitational lensing. When astronomers stare at a galaxy cluster warping the light of distant objects behind it, they're not just seeing an optical illusion, they're reading the universe's most honest scale. The deeper the dent in spacetime, the heavier the cluster must be. But here's the jaw-dropping part. Add up all the visible stars, gas, and dust in these colossal structures, and you'll barely scratch 15% of their true mass. The rest. A gravitational signature written in bent light, proving dark matter's dominance in the cosmic ledger. Take the famous L cluster, one of the most massive structures known. Through traditional telescopes, it appears as a scattering of brilliant galaxies against the blackness of space, impressive but not extraordinary. But map its gravitational lensing effect and the truth emerges. The way it stretches background galaxies into luminous arcs reveals a total mass equivalent to 3 million billion suns, enough to bend spacetime into a natural telescope, so powerful it magnifies objects 13 billion light-years behind it. The visible galaxies, just decorative sprinkles on an invisible cake. This cosmic weighing technique doesn't rely on assumptions or models, it's direct measurement through geometry. When light from a distant galaxy passes near a cluster, its path bends by an amount precisely tied to the cluster's total mass. The mathematics is elegant. the more distorted the background galaxy appears, whether stretched into an arc, duplicated into multiple images, or brightened unexpectedly, the more massive the foreground cluster must be. It's like watching how deeply a bowling ball sinks into a trampoline to guess its weight, except the trampoline is spacetime itself, and the bowling ball is a conglomerate of hundreds of galaxies. What's astonishing is how this method exposes the universe's hidden architecture. Weak lensing surveys, which analyze subtle distortions in millions of galaxies, have mapped dark matter's cosmic web in 3 dimensions, revealing vast filaments connecting galaxy clusters like invisible bridges across the void. These maps show dark matter isn't just haloed around galaxies. It forms an intricate scaffolding that guides where luminous matter collects, like grooves in a cosmic record determining where the needle of star formation lands. The implications rewrite our cosmic inventory. Before lensing, astronomers estimated the universe's mass by counting stars and gas, a bit like guessing a city's population by counting lampposts. Now lensing reveals that for every kilogram of visible matter, there's at least 5 kilograms of dark matter exerting gravitational pull. In some galaxy clusters, that ratio jumps to 30-1, making our familiar atoms cosmic afterthoughts in a dark matter-dominated universe. Perhaps most remarkably, this cosmic scale works across unfathomable distances. When astronomers measured lensing distortions in the ultra-deep field, a patch of sky no larger than a grain of sand held at arm's length, they weighed dark matter's distribution across billions of light years, tracing how it's changed as the universe expanded. These observations confirmed dark energy's existence independently of supernova studies, proving the universe's acceleration wasn't just a fluke in the data. The true power of lensing as a scale lies in its impartiality. Unlike methods that rely on a galaxy's brightness or stellar motions, which can be skewed by dust or unusual orbits, lensing measures pure gravity's grip on spacetime. It doesn't care if matter emits light, absorbs it, or ignores it entirely. This has led to surreal discoveries, like dark galaxies with hardly any stars but enough lensing heft to rival the Milky Way, or rogue black holes drifting unseen until their gravity briefly magnifies a star's light. As next-generation telescopes like the observatory come online, this cosmic scale will grow exponentially more precise. Imagine weighing every galaxy cluster in the observable universe, or detecting dark matter's microscopic ripples around individual stars. Each measurement is a vote in the ongoing referendum on our cosmic composition. And so far, the verdict is clear. The universe we see is just the shimmering surface of a vastly darker, stranger reality. In gravitational lensing, it's the only scale honest enough to weigh what we cannot see. Gravity's ability to bend light isn't just a cosmic spectacle, it's a mathematical symphony, where every warped galaxy and stretched arc follows equations etched into the fabric of reality. At the heart of it all is deflection angle formula, a deceptively simple equation that predicts exactly how much starlight will curve when passing near a massive object. Picture a beam of light skimming the sun's edge. According to the math, its path will deflect by a tiny but precise amount, 1.75, or roughly the width of a penny seen from 2 miles away. That number isn't arbitrary. It's derived from fundamental constants like the speed of light and the gravitational constant, woven together by the unshakable logic of relativity. But how does this translate to the dramatic rings and celestial mirages we see in telescope images? Enter the lens equation, the unsung hero of gravitational lensing. Think of it as a cosmic recipe with 3 key ingredients: the distance from Earth to the lensing object, the distance from the lens to the background light source, and the mass of the lens itself. Mix these together, and the equation spits out predictions for where and how distorted images will appear. It's why astronomers knew exactly when to expect that delayed 5th image of supernova. The math had already charted spacetime's curves like a subway map, tracing light's detours around galactic gravity wells. To grasp why light bends this way, imagine diving into a swimming pool. As sunlight enters the water, it slows down and changes direction, a familiar trick called refraction. Gravity warps light similarly, but instead of water molecules causing the slowdown, it's the sheer weight of mass denting spacetime itself. The denser the object, the steeper the dent, and the sharper the light's curve. A galaxy cluster's immense gravity creates such a profound dip that light can loop around it like a marble spiraling around a funnel's edge, creating those surreal rings and arcs. What's breathtaking is how these abstract symbols on a page spring to life in the cosmos. Take the iconic cross, 4 perfect copies of a single quasar arranged around a foreground galaxy. The lens equation didn't just suggest this could happen, it precisely predicted how the images, spacing, and brightness would reveal the galaxy's hidden dark matter halo. When telescopes confirmed these predictions down to the percentage point, it wasn't just a win for relativity. It was proof that math is the universe's mother tongue. For number lovers, the real magic lies in the details. Tiny discrepancies between lensing observations and equations can unveil revolutionary physics. Some galaxy clusters bend light slightly more than their visible mass should allow, hinting at exotic dark matter behaviors. Others show anomalies in image distortions, sparking debates about whether constants need tweaking for extreme scales. Every decimal place in these calculations isn't just academic. It's a potential doorway to new cosmic truths. So the next time you see an image of a lensed galaxy, remember, those elegant arcs aren't accidents. They're the universe solving an intricate geometry problem in real time, with gravity as its compass and light as its pencil. And thanks to mathematics, we're not just spectators to the show, we've cracked the code to read the script. Wormholes have long been the stuff of science fiction, cosmic shortcuts where a starship might leap across the galaxy in the blink of an eye. But what if these spacetime tunnels aren't just fantasy? Gravitational lensing offers a tantalizing way to hunt for them, not with futuristic probes, but by decoding the subtle distortions they'd leave in the light passing by. Imagine a distant star's light splitting into not just 2, but multiple images around a suspected wormhole's mouth, each version slightly different in brightness or even color. Unlike ordinary lensed quasars, where duplicates are near identical, a wormhole's twisted geometry could stretch some light paths through its throat while others curve around the outside, creating mismatched echoes of the same object. The math behind this is as elegant as it is mind-bending. A traversable wormhole, unlike a black hole, wouldn't crush light into oblivion. Instead, its throat might act like a funhouse mirror, bending and filtering light without trapping it. Some models predict a telltale asymmetry in the resulting images. One might appear as if drained of energy after traversing the wormhole's gravitational hills, while another could emerge, compressed by the journey. Even stranger, certain wormhole configurations might split light into time-delayed copies, like cosmic postcards arriving out of order. While no confirmed wormhole has ever been found, lensing gives us a way to search without needing to dive into the abyss. Astronomers could scan the sky for anomalous lensing events, places where the bending of light defies the predictions of equations for ordinary matter. Consider a galaxy cluster that warps background light too much, as if hidden mass lurks where telescopes see nothing. Most would chalk it up to dark matter, but what if the excess distortion comes from a wormhole's gravity, its entrance camouflaged among the stars? Or picture a star that flickers in a way no event can explain, its light dimming and brightening as if something tunnel-shaped is drifting silently between us and it. The wildest possibility, wormholes might not even require exotic matter to stay open. Recent theories suggest certain quantum effects or higher dimensional geometries could stabilize them naturally, leaving lensing as our only way to detect their presence. Projects like the observatory, which will image the entire southern sky every few nights, could stumble upon these anomalies by accident, flagging warped starlight that doesn't fit the usual cosmic mold. For now, wormholes remain in the realm of theory, but so did black holes once, and gravitational waves and dark energy. The universe has a habit of taking our wildest ideas and revealing they've been true all along. If wormholes are out there, lensing won't just find them. It'll rewrite our understanding of spacetime's flexibility. Until then, every strange lensing anomaly is a breadcrumb, one that might lead us to the cosmos' most elusive shortcuts. After all, the line between science fiction and science fact has always been thinner than we think, and gravitational lensing might be the thread that pulls it taut. Lensing doesn't just bend the light our eyes can see, it twists the entire electromagnetic spectrum, revealing hidden layers of the cosmos depending on how we choose to look. While optical telescopes show us the graceful arcs of lensed galaxies, radio arrays like ALMA pierce through the cosmic dust that shrouds their star-forming hearts. In 2017, ALMA spotted a lensed galaxy so cloaked in dust it was nearly invisible too. But in radio wavelengths, its light blazed through, exposing a frenzy of stellar nurseries churning out new stars 1,000 times faster than the Milky Way. The kicker: the lensing effect amplified the galaxy's faint radio glow 32 times, giving astronomers a crystal-clear view of chemistry in action. Carbon monoxide molecules swirling in vast clouds, the raw material for future planets. Switch to X-rays and the story turns fiercer. When trains its gaze on a galaxy cluster acting as a lens, it doesn't just magnify the objects behind it, it maps the scorching plasma within the cluster itself. This million-degree gas, too hot to emit visible light, glows brilliantly in X-rays, revealing how the cluster's gravity warps not just light, but the very fabric of its environment. Take 2163, where X-ray jets from supermassive black holes are bent into bizarre curves by the cluster's gravity, like cosmic fountains twisted by an unseen hand. These distortions aren't just visual spectacle. They let scientists weigh the cluster's total mass, including the dark matter lurking between those glowing gas clouds. Then there's infrared, the wavelength that peers through cosmic time. The James Space Telescope's infrared vision, paired with lensing, spots galaxies so ancient their light has stretched into infrared wavelengths from the universe's expansion. In its first deep-field image, a lensed galaxy nicknamed the Sparkler appeared not as a single smudge but as multiple ruby-red dots, each a duplicate image by a foreground cluster. But here's the twist: those dots weren't stars. They were globular clusters, relics from the universe's first 2 billion years, whose faint glow would have been lost without both infrared sensitivity and lensing's amplification. The real power emerges when these wavelengths collaborate. A single lensed galaxy might reveal its stars in visible light, its dust in radio, and its black hole's fury in X-rays. A multi-wavelength dissection impossible without gravity's magnifying effect. Even gamma rays, the universe's most energetic light, can be lensed. In 2014, Fermi detected gamma-ray photons from a distant blazar arriving minutes apart, their paths bent differently by an intervening galaxy. That delay, measured in the highest energy light possible, became a stress test for relativity itself. What's clear is this: the universe's grand illusions don't play favorites with wavelength. Whether it's radio whispers from stellar nurseries, X-ray screams from black holes, or infrared echoes from the cosmic dawn, lensing ensures we're not just seeing the cosmos, we're seeing it in every possible light. And with each new spectrum we unlock, gravity's funhouse mirror reflects back another piece of the puzzle. From scribbles on a chalkboard to breathtaking deep-field snapshots, gravitational lensing has done more than just bend light. It's bent our very understanding of the cosmos. What began as a curious prediction in the equations of relativity has blossomed into one of astronomy's most powerful tools, revealing a universe far stranger and more interconnected than we ever dreamed. Think about it, the same force that pulls an apple to the ground also sculpts the light from galaxies so distant their light has traveled since the dawn of time. It's as if the universe handed us a pair of glasses to see its hidden layers, dark matter's invisible threads, the echoes of ancient supernovae, even the possibility of worlds beyond our cosmic horizon. This journey from theory to revelation is a testament to human ingenuity. When Arthur's eclipse experiment first confirms wild idea in 1919, no one could imagine that a century later, we'd be using spacetime's curves as a cosmic microscope. As Frontier Fields, the Event Horizon Telescope's black hole portraits, the delicate dance of flashes, each breakthrough has rewritten the rules of what we thought possible. And the most thrilling part, we're just getting started. With telescopes like the Observatory and Euclid coming online, lensing is poised to expose even deeper secrets. The nature of dark energy, the distribution of rogue planets, perhaps even anomalies that hint at physics beyond. But beyond the science, lensing reminds us of something profound. The universe loves a good illusion. Those shimmering stars on a clear night, some aren't stars at all, but galaxies stretched into celestial mirages by invisible hands. The quiet darkness between them, not so empty but teeming with matter we can't see, detected only by how it warps the light passing through. It's a humbling thought. No matter how much we learn, the cosmos always keeps a few tricks up its sleeve. So as you step outside and look up tonight, let your eyes linger on those distant points of light. Somewhere out there, a photon that left its home billions of years ago is curving around a galaxy cluster, twisting through spacetime's folds to reach your retina. That connection between your gaze and the universe's grand distortions is the true magic of lensing. It's not just about the science, it's about wonder. Keep asking questions, stay dazzled by the cosmos's illusions, and who knows? The next great cosmic revelation might come from an amateur spotting an odd arc in a telescope image, or a student scribbling equations that bend our perspective all over again. The universe is waiting to surprise us. Let's keep looking.